a short duration interaction between two or more bodies where large forces act. So think about a collision where the shape does not change. There is no deformation. So first I am talking about elastic collision. So that's why I've taken two billiard ball here. Let's say there are two lumps of clay and you throw a clay towards the another and they stick together. Give you an idea that when inelastic collision happens, then what exactly would be the equation governing the motion. Hello students, welcome in today's class. In today's class, we are going to learn about collisions. Alright, so this is a video in continuation where we are learning about forces, and of course collision is an example where large amount of forces operate. But yes, they do operate for a very short duration of time. So I hope you understand the difference between collision and any other application of force. So for example, when you are pushing a table in front of you, that cannot be regarded as a collision in that sense. But when you hit a ball with a bat, then that of course is a collision. What is the difference? The force operates for a very short duration of time, but then there is a huge amount of force that is applied, isn't it? Think of many other examples. Let's say two balls colliding like in billiards, or maybe two cars crashing with each other, or God forbid not, but what if an asteroid collides with the earth? So these are all situations where large amount of forces operate, isn't it? So let's study and discuss the physics behind collision one by one. First we'll start with the technical things and then see the corresponding numericals. Alright, so put down the heading collisions. So let me read out the basic definition of collision: a short duration interaction between two or more bodies where large forces act, causing a finite change in their momenta. So I hope you are able to relate with this definition. Then the classification. Alright, so before the classification, let's discuss that through an example. So let's say there is a collision called elastic collision. What are we trying to say here? So elasticity is basically a property to state that a body regains its original shape and size. So think about a collision where the shape does not change. There is no deformation. Think of an example like two billiard balls colliding. There is no deformation whatsoever. So that can be regarded as an elastic collision. And when that happens, there is no energy loss majorly in the form of deformation. Alright, so what are elastic collision? An elastic collision occurs when two bodies collide and there is no permanent deformation. Alright, so you might relate elasticity with something which is flexible, but that's not the case here. Elastic collision means when there is no deformation. So something that is very rigid can be taken as elastic collision, or maybe collision between the gas molecules in your room colliding with the walls of your room. That can also be regarded as an example of elastic collision. Alright, and hence there is no net loss in kinetic energy. Example that I was talking about, collision of two billiard balls. Alright, so put down the heading collision and then write down the basic definition and the two types of collision, that is elastic and inelastic. So I hope you've written this down. Now let me talk about the inelastic collision. So obviously it's going to be vice versa now, and there has to be some permanent damage or deformation. So an inelastic collision is a type of collision where only the momentum is conserved, but the kinetic energy of the system is not conserved, as some part of that is going into the deformation, right? So a perfectly inelastic collision occurs when objects stick together after the collision. So we'll discuss that. But right now, let's just focus on in these two categories, elastic and inelastic. Elastic when there is no permanent loss of energy, while inelastic when there is some loss of energy due to the deformation. But now you might, just argue that even in elastic collision, like two billiard balls colliding, there has to be some loss of kinetic energy. Why so? Because of course, sound is produced. Of course, some heat might also be produced, but that component of energy loss is way too small to be taken into account. That is why whenever we say elastic collision, we always say that there is no permanent deformation, alright? Secondly, let me talk about the whole scenario in detail. What exactly happens when two bodies collide? Think about a slow motion video of two balls colliding. What do you reckon? What happens? So the initial part of the collision, the bodies are going to deform each other. The deformation is going to rise. The force is going to rise as seen in this graph. But then after a point, they start detaching from each other. They start moving away from each other. And that is when the force starts decreasing. So if you go into that detail, what happens during that fraction of a second, you should realize that the force versus time graph should look like this. Or maybe just to make it a little more simple, you can take it as a triangle, isn't it? So the force increases first and then it decreases, and a pattern like this is followed. And if from the last class, where last classes that we have been discussing, if you remember, we have talked about a physical quantity called impulse. So impulse is something that you should of course associate with collision, isn't it? Impact, impulse, it is a perfect term that applies to collision, isn't it? So what happens here is very difficult to monitor the force and the time, so we rather do, we rely on impulse. How? Let's find out. So impulse, if you remember, is the product of force and the time duration for which the force acts, which is nothing but the area under this curve, area under F versus the graph or curve, isn't it? So the area under this will give you the impulse, and that will tell you how fierce the collision was, right? So impulse is the product of force and time. All right. The next thing, it is also equal to the change in momentum. As you remember that force is given by rate of change of momentum. This is Newton's second law for you. So when I am discussing all this, I am assuming that you're well versed with the basic concepts of force and the Newton's laws. And if you're not, then it is highly recommended that you go back to those videos, see the basic classes first, and then return to this video. All right. So force times time is nothing but the change in momentum. That is what we call as impulse. So keep this in mind, because we are going to talk about this quite a few times now in this video. So keep that in mind. All right. So this is collision. The classification, I hope it's very clear. Elastic and inelastic. Copy down the important stuff, then we move forward. All right. Now let's do the mathematical part of it. One by one, let's discuss the collision. So first, I am talking about elastic collision. So that's why I've taken two billiard ball here. I hope you do understand that when two billiard balls collide, there is no deformation. This is what elastic collision is. So the first thing, again, I'm going to write that there is no deformation. All right. So there is no deformation. Hence, there is no loss of kinetic energy. Okay. Secondly, momentum is conserved as well. Momentum is conserved, isn't it? Let's understand this. Momentum is conserved. Now think about this, that ball 1 is going to apply a force on ball 2 and ball 2 is going to apply a force on ball 1. But if you think about Newton's third law, then the force applied on ball 2 is going to be equal and opposite to the force applied on ball 1. So what does it mean? That if you combine them as one system, then there is no external force. There is no external force. So yes, the momentum of the two balls individually would change, but the overall momentum would never change. In fact, that is something which is general and applies to all kinds of collision. Only the energy conservation, that is applicable for elastic collision. So without wasting time, let's do this. Initial momentum is equals to final momentum. This is a very major application of principle of conservation of momentum, that there is no external force and therefore momentum remains conserved. All right. So let's assume that the mass of this is m1, mass of this is m2, velocity is u1, velocity is u2. So I'm using u for velocities before collision as we normally do, and let's assume that their velocities become v1 and v2 after collision. Alright, so without wasting time, m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. Very simple equation. I hope you should be able to relate with this. But one more thing, I would like to rewrite this. How? m1 v1 minus u1, think about this, is equals to m2. So I am taking the terms of 1 on one side and 2 on the other side. So this is going to be m2 u2 minus v2. Alright, let's call it 1 dash, as this is no new equation. It is just the rearrangement of the previous equation. Why are we doing that? You'll quickly find out. Now, can we also write final kinetic energy is equals to initial kinetic energy? Yes, because that applies to this particular type of collision. Alright, so half m1 v1 square plus half m2 v2 square, that's the formula for kinetic energy, I hope you know that, is equals to half m1 u1 square plus half m2 u2 square. Alright, now the half factor will cancel out and we can write m1 v1 square minus u1 square is equals to m2 u2 square minus v2 square. See, ultimately, majorly what happens in most of the questions is you need to predict the velocities after collision. So we assume that v1 and v2 is something that we will predict using the concepts of physics. But I would like to talk about one more thing here. What is that? That if we use a mathematics identity, that is a square minus b square is a minus b times a plus b, let's apply it to this, then you would understand that when we rewrite this as this, u2 minus v2 into u2 plus v2. Now, if you look at this closely, then m1 v1 minus u1 is equal to m2 u2 minus v2. What does this give you? This gives you v1 plus u1 equals to u2 plus v2. What is so fascinating about this? Let's find out. If we rewrite this one more time, then this is going to be u1 minus u2 is equals to v2 minus v1. Now think about this. What is u1 minus u2? So this can be regarded as the velocity of approach. So very simply, I have assumed that both are moving in the same direction. Let's say this is moving with 10 meter per second and this is moving with 13 meter per second, 1, 3. Then with what velocity ball 1 is approaching ball 2? Answer is going to be 3. So we can call this u1 minus u2 as the velocity of approach. We can call this as the velocity of approach or the approach velocity. With what velocity this ball 1 is approaching ball 2. That is going to decide how devastating the collision is going to be. Imagine if this is moving with hypothetically 50 meter per second and this is moving with 52 meter per second, collision won't be that devastating. Why? Because it is not moving at a very high pace with respect to the first ball. So that is something that is going to decide how impactful the collision is going to be. Alright, now what is v2 minus v1? We can call this as the velocity of separation. So keep this in mind, it's going to be helpful for you that elastic collision, momentum is definitely conserved, it is conserved in all sort of collision, energy is also conserved in this type of collision, and then we have a new thing coming up, that velocity of approach is equals to the velocity of separation. Copy down the important stuff, pause the video, copy it down, and then we move forward. Alright, so I hope you've copied it down. Next, let's talk about the perfectly inelastic collision. Now what happens here is, let's say there are two lumps of clay and you throw a clay towards the another and they stick together. So if you think about the slow motion situation, what would have happened? So maybe the lump 1 would have deformed the lump 2, but then they never detach. That means the maximum deformation when it happened, that persists, that retains. That means there is no further, loss of, in a way the deformation is not lost again and it survives at the peak value. So can we say that the two combine as one after collision? So if this is, let's say, m1, this is, let's say, m2, then this combined mass will be m1 plus m2. And if this velocity was u1, this was u2, then this combined velocity is going to be v. So definitely now the energy is not conserved because the deformation happened and it did not, get corrected, and therefore we can say that there is definitely a loss of kinetic energy. So this time there is a permanent loss of kinetic energy, hence we cannot use the equation of kinetic energy conservation. But still external force is 0, which means initial and final momentum remains conserved. Alright, so let's use this. Let's write P final is equals to P initial. So P final is going to be m1 plus m2 times v, isn't it? And P initial is going to be m1 u1 plus m2 u2. Alright, so I am again assuming all are moving in the right direction. If any of them is moving towards the left, you know what to do. Just put the value with a negative sign, isn't it? So the value of v turns out to be m1 u1 plus m2 u2 over m1 plus m2, isn't it? So that's the final velocity for u. What else? Now, in fact, sometimes in some situation in problems, they might also ask you the kinetic energy loss. So let's calculate that. So the loss of kinetic energy here is going to be K initial minus K final. So let's do that. So what is K initial? So you would say half m1 u1 square plus half m2 u2 square. And what is going to be the final kinetic energy? So you would write half m1 plus m2 into v square. So we calculate the value of v from here, we put it over here, and we calculate the loss in kinetic energy. Easy, right? So this energy goes into the deformation, right, in the form of elastic potential energy, if you may call it like that, which you might have learned in your previous classes. If not, we are going to learn that in future, right, in the upcoming videos. Alright, so that's about the extremes. So what extremes have we covered? First, when there is no deformation. Second, when there is maximum deformation. So think about two cars colliding. They collide, deformation happens, but then they also detach from each other. So some deformation extent reduces. But then treating that mathematically becomes very complex. So we would try to hop between these two categories only. So we will either classify the collision as elastic, or we will classify them as perfectly inelastic. In some other video, we might talk about, coefficient of restitution, which would be optional. Just for your extra knowledge, if you wish to do that, we can. But right now, we are not focusing on that part, and we are only discussing the two cases where we can easily treat the situation mathematically. All right. So copy down the important stuff, then we move forward. All right. Still, I will just give you an idea that when inelastic collision happens, then what exactly would be the equation governing the motion, right? So if this was u1, this is u2, as you would realize that momentum still remains conserved even if there is a loss of energy, because the net external force is 0, right? So let's assume that velocities become v1 and v2. So you can still apply momentum conservation, but you cannot apply kinetic energy conservation. All right. So keep this in mind. Another thing, just for the sake of knowing it, that in case of elastic collision, as you have just understood, the velocity of approach is equals to the velocity of separation, isn't it? The velocity with which separation happens. While in case of perfectly inelastic collision, what we have realized is that v2 is equals to v1. So they both combine as 1, and we can say that velocity of separation becomes 0, isn't it? This is one more benchmark that you can keep in mind, that in case of elastic collision, the separation velocity is as much as the approach velocity. In case of perfectly inelastic collision, there is no separation velocity. So in case of inelastic collision in general, the velocity of separation is less than the velocity of approach. All right. So this is about, this is what Newton predicted, and that is somehow accommodated in coefficient of restitution, but that is something we are not discussing in this class. All right. So I hope you understand the third category, that is in general between elastic and perfectly inelastic collision. Okay. Copy it down, then we move forward. All right. So now let's take a couple of examples. Two masses moving in a straight line towards each other collide as shown. Okay, so there is a 4 kilogram moving with 24, a 12 kilogram moving with a velocity 2 in the opposite direction. So this is the situation before collision, and what we have to answer is find the velocity, magnitude and direction of the heavier ball after collision. All right. So here the question is very easy. We just have to apply conservation of momentum. We don't know if the collision is elastic. In fact, they are asking us to do that. State if the collision is elastic. All right. So let's do it. So initial momentum is going to be 4 times 2 for this, 4 times 24 for this one, right, because it is in the positive direction. And for this one, it is going to be 12 times minus 2 because it is in the left direction. What about this? So this one, that is 4 kilogram, the velocity becomes minus 3. So it collides and it starts retracing its path. It goes in the backward direction. All right. What about this one? So let's assume that the velocity is v after collision, as you would. So this becomes 96 and this is like 24. This is going to be 12 minus 12 and this is going to be 12v. So let's solve this. So this is going to be 96 minus 12, that is 12v. So this becomes 84 equals to 12v, and if we solve it, we obviously get 7 meter per second. Since we are getting plus 7, that means the velocity of this after collision is going to be to the right, isn't it? Easy. Now they are asking if the collision is elastic. One way of checking that is check the kinetic energy before collision and check the kinetic energy after collision. So what is the initial kinetic energy? You would write half times 4 times 24 square for this one plus half times 12 times 2 square for this one. Here the negative sign does not count because ultimately we are going to square the velocity, so the sign won't matter. We can straight away take it as only the magnitude, that is the speed. So this is the initial kinetic energy. Let's do this calculation very quickly. So this is going to be, let's say, 24 times 24 times 2. So this is 1152, and this of course is going to be 12 times 2, that is 24. So plus 24, this is giving me 1176 joule, isn't it? Let's check for the final one. So the final kinetic energy is going to be half times 4 times 3 square plus half times 12 times 7 square. All right, so let's do this calculation very quickly. So this is going to be 2 times 9, that is 18, and this is going to be 6 times 49. So 6 times 49 is giving me 294 plus 18 is giving me 312 joule. Clearly there is a huge loss of energy. From 1176 joule, it has become only and only 312 joule. So final kinetic energy is less than initial kinetic energy. I hope your answer matches with mine, and this is not an elastic collision, it is an inelastic collision. All right, copy this down, then we move forward. All right, so a mass of 6 kilogram moving at 4 meter per second collides with a stationary mass of 8 kilogram and sticks to it. How much kinetic energy was lost in the collision? So let's do this very quickly. We would write P final is equals to P initial. So P final, as you may imagine, since both are sticking together, it's going to be 14 kilogram times V. So I hope you understand. Let's draw this diagrammatically. Let's say this is a 6 kilogram. So you have to pause the video and try the question first and then look for the solution. All right. So this was moving with 4 meter per second and this was 8 kilogram, which was at rest. Why? Because they've written it is a stationary mass, and after collision they stick. That means it becomes a 14 kilogram, and let's say the velocity becomes v. Alright, so this is going to be 14v, that is the final momentum, and the initial momentum is going to be 6 times 4. This does not carry any momentum because it was at rest. So the value turns out to be 24 by 14. Alright, so let's do this calculation very quickly. 24 divided by 14, what we are getting is 1.71 meter per second. So let's calculate the initial kinetic energy that the system was possessing. That's going to be half times 6 times 4 square. So that is like 6 times 8, and that is going to be 48 joule. Alright. What about the final kinetic energy? So that is going to be half times 14, as the combined mass becomes 14, times 1.71 whole square. So that's going to be 7 times 1.71, and that is giving me approximately 12 joule. Okay. So what is the loss? So of course the loss is going to be K initial minus K final, and that is going to be 48 minus 12, that is going to be 36 joule, isn't it? Easy, no problem. This is an example of perfectly inelastic collision. Copy it down, then we move forward. Another example. Now what are we doing here? A bullet of mass 0.08 kilogram moving at a speed of v gets embedded in a block of mass 2 kilograms. So take this as a bullet. It is moving towards a block, and then it gets embedded in the bullet. All right, in the block, sorry. Now this is the initial state, this is the intermediate state, and this is the final state. Now why is this an intermediate state? Let's find out. So the bullet first collides with the block, gets embedded in it, imparts some momentum to the block, because of which it rises, and that is what we have to find out. How much does it rise, isn't it? This is what they are asking. The block and the bullet move together and stop when the string makes an angle 37 degrees. So they have given us that it rises up to 37 degrees, and then they are asking us the velocity v. Give it a try, then we move forward. Alright, so I hope you've paused the video and tried it, and now let's see what can be done here. So the first part, when it collides and gets embedded in it, can we take it as a perfectly inelastic collision? Yes. Why? Because the two stick together. So let's assume that this flies off with the velocity v1. Because of this v1, this will rise. How much does it rise? Let's find out. So the length of the string is 1.5. Alright, so this length is 1.5 meter. Okay, so can we calculate this now? Of course, yes. This is going to be 1.5 cos 37. So let's do this calculation. 1.5 cos 37. That's giving me 1.5 times cos 37. That's giving me 1.2. All right. That means this rise is going to be how much? So from 1.5 it has become 1.2. So this rise of course is going to be 0.3. So now are you understanding what is happening? First collision happens, then it starts rising. That means it loses kinetic energy and gains potential energy. So if we apply initial kinetic plus initial potential to final kinetic plus final potential between points, let's call this A, let's call this B, and let's call this C. So where are we applying this? Between B and C. Because once the bullet gets embedded in the block, it moves and just converts the kinetic energy to the potential energy, right? So what is the kinetic energy? Half times the total mass, that is going to be 2.08. I hope you understand why it is 2.08, because the mass of the block and the bullet gets added up, and that is like V1 square is equals to 2.08 times gravity mgh, right? So I hope you know the expression for potential energy, which I am denoting by U. So that's going to be mgh. So kinetic energy I am denoting by K, and potential energy I am denoting by Q. So what are we getting from here? 2.08, 2.08 cancels out. So first let's do this calculation. 2 times 9.8 times 0.3, alright, and then square root the answer. So we are getting the value of V1 as 2.42. This is the velocity after this system has collided, this bullet has collided, and they are combining and moving as one. But the question is asking us this velocity. What do we do now? So since this is a perfectly inelastic collision, so between A and B, let's apply the principle of conservation of momentum. Alright. So what is the momentum the bullet is possessing? So it's going to be 0.08 times V, and the block did not have any momentum initially. Now the two combine and they become equal to a mass of 2.08, and the velocity becomes V1. This V1 we already know, so let's put the value, and this is going to be 2.08 times V1, that is 2.42. Alright, so the velocity V turns out to be 2.08 times 2.42 divided by 0.08. Alright, so this turns out to be approximately 63 meter per second. This is the velocity with which the bullet struck the block, imparted momentum to it, and then they combined as one mass and they started rising. It's a good example. We are applying principle of conservation of energy also, and we are making use of perfectly inelastic collision also. Alright, copy it down, then we move forward. Alright, now let's talk about two-dimensional collision. Okay, so what is this two-dimensional collision? So think about, so far we have been discussing collision as head-on. So we have always assumed that the velocities lie along the line joining the two masses. But sometimes purposely you hit let's say something at an angle so that you obtain motion in two different directions. Once they start moving in two different directions, that is like oblique collision for you, isn't it? So this is two-dimension collision. Let's do an example to understand how situation would change. So let's say this is a 2 kilogram ball and it is striking a 4 kilogram ball at rest. But the catch here is that the velocity that this is possessing is not exactly aligned with its center. It is slightly away. Due to that, this ball moves in one direction, the previous ball moves in some other direction, and let's say we have to predict the value of V and the angle at which this moved, right? So let's call this M1 and let's call this M2. So initially we would write again the same thing, that is the principle of conservation of momentum, but we will bifurcate it in the two directions, that is X and Y. So the velocity that this mass is possessing in X direction is 6, so the momentum is going to be 2 times 6, while for the second one it is going to be 0 because it was at rest. Now think about this. This ball will have a velocity of 4 cos 20 degree, right? And this component is going to be 4 sin 20 degree. I hope you know how to resolve vectors in the X and Y direction, right? Similarly for this one, it is going to be V cos theta and this is going to be V sin theta, isn't it? So let's use this equation and conserve momentum in X direction. What are we going to get? So we are going to get this ball had a mass of 2 kilogram. So let's write 2 times 4 cos 20, isn't it? Plus 4 times the mass of the other ball is 4 kilogram times V cos theta, isn't it? This is the first equation that you have in V and theta. Secondly, you can conserve momentum in Y direction, isn't it? So P initial in Y is equals to P final in Y. So the only thing that changes in case of two dimension is that now you're writing momentum conservation also in two different dimensions. First in X and then in Y. Now the momentum in Y direction, in fact there is no momentum in the Y direction, and that is why the both terms are 0. Now what about the final momentum? The final momentum is going to be, let's say for this one, it is going to be 2 times 4 sine 20. That is for this one. And what about this? The mass is 4 kilogram and the velocity is going to be minus v sine theta. I hope you understand why have we put a minus sign here. That is because it is moving in the negative y direction. This is the second equation. So this gives me 8 sine 20 is equals to 4v sine theta, isn't it? While this equation gave me, let's solve this very quickly. Let's solve this very quickly. So this is 8 times sine 20, isn't it? So this is giving me 2.736 and let's divide it by 4. So that's giving me 0.68. Alright, so v sine theta, I am getting it as 0.68. Now let's solve it for this. So this is 8 times cos 20. So that is, and 12 minus this value. So 12 minus the answer, that's giving me 4.5. So 4.5 and then divided by 4 again. So 4.5 divided by 4, that's giving me 1.125. Alright, so this is the value of v cos theta. Now if you want theta, you just divide the two equations, then you are getting 0.68 divided by 1.125 and what I am getting is as 0.6. The value of tan theta after solving, dividing, I am getting as tan theta is equals to 0.6 and then you can calculate the angle as well. Tan inverse the answer is coming out to be approximately 31 degrees. Alright, so it is going to be 31 degrees. Now you use this value to calculate the value of v. So that's going to be 1.125 divided by cos 31. Alright, so what I am getting is v is 1.312. So what have I done here? It's no big deal. I have just applied the principle of conservation of momentum, but this time I have done that in two different parts. There is a lot that is done here. Think about it, pause the video, try it yourself, then we move forward. Alright. Alright, now let's take one last example before ending today's class, again on collision. So, a ball of mass m rolling on a floor with speed v rebounds from a wall with an unchanged speed at an angle theta to the wall. Alright, so this is the situation. There is a wall and it collides and then it rebounds. Alright, so the diagram shows the top view of the collision. Delta p is a vector representing the change in linear momentum of the ball. What is the magnitude of delta p? So give it a try, So the velocity is going to be, let's say, v cos theta in the x direction here, and it is going to be v sin theta in the y direction, isn't it? So I hope you are able to resolve the vectors here, and then it rebounds. Of course it is going to rebound with the same speed. Why do I say so? Because the angle does not change, and if angle does not change, that means the horizontal component should remain the same, as the wall can only apply a force in the y direction, isn't it? So the velocity does not change, and we can write, let me change the color here. Let's say the velocity here becomes v cos theta again, but now the y direction velocity will become v sin theta in the opposite direction, right? So the x direction, according to this diagram, the momentum is not changing, but there is only a delta p in the y direction. So let's do that. Let's do that very quickly. So delta p, it is going to be p final minus p initial, which is only happening in the y direction. So what is p final? That is going to be mv sin theta minus p initial, that is going to be m, and then minus v sin theta. Why should I put a minus sign? Again reminding you, since it is in the downward direction and we always take upward as positive. So this value turns out to be 2mv sin theta, isn't it? So what is going to be the answer for this? The answer for this is going to be B, that is 2mv sin theta. What about the direction of delta p? Which arrow represents the direction of delta p? Think about it, A, B, C or D. So as clearly the value is turning out to be positive and in y direction, so the ball has suffered an impact and it experienced a force in the y direction. That is why the answer should be option D and not B. A and C anyways were not the choice. The only choice we had was B and D, but we are writing delta P for the ball. So it is going to be in this direction. If we talk about the wall will suffer the same impulse in the opposite direction, then the answer would have been B. But we have to write it for the ball and therefore the answer is D. Alright, so this is what we have discussed today about collision, and I hope you were able to grasp most of the stuff. But don't worry if you don't get some of the things. We will get to understand them way better when we are going to use these concepts in the previous year question series. So very soon we are going to start with the previous year questions where we will apply all this. Alright, so I hope you will keep learning about this and try some more questions, and I will see you very soon next time. Bye bye, happy learning. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.